time about the wind-driven circulation in the the wind-driven circulation in the ocean, which is associated to the Ekman transport or Ekman pumping or suction, which is associated to a typical wind regime over the ocean, starting from the equator to the polar areas where you have the exchange between the westerlies and easterlies. We are in it. Our area is westerlies, right? Because we have all the time disturbances coming from west, and this is the area of westerly. So we are here. Okay. So this is what we talked about. I just mentioned before that if we have the convergence, or if we have a convergence or divergence, we have this type of horizontal distribution of isopycnals of sea surface and pressure isolines and sea surface, how it is distributed in space. If you have the convergence, then the pressure lines are like this. This is the form of the pressure line. The sea surface is you have a bulb at the sea surface because you have the convergence, and therefore, although there is the vertical movements downward, there is some mass presence there, which makes the sea surface going upward. And this is the opposite, where you have the divergence, and you have this form of the sea surface, and the density isopycnals are structured like this. So these are the anticyclonic warm core eddies or cyclonic cold core eddies, and but they can be due simply also to the wind field. If you have the divergent wind field, if you have the curl of the wind field such that creates the divergence or convergence, as a result of this would be anticyclonic or cyclonic motion. But these, in this specific case, warm core eddies and cold core eddies are those which appears along the frontal area in, for example, the Gulf Stream. The similar thing is, as I told you before, in the atmosphere you have cyclonic or anticyclonic motion, which are due to the instabilities over the frontal polar front, and they essentially inside structure, interior structure of these cyclones or anticyclones is exactly this one. So we have a equivalence between whatever is happening in the atmosphere is happening in the ocean, except what, as I told you before, there are differences in a space scale, spatial, but also in a temporal scale. This is the cross section, what we have also seen before in when we have trade winds and westerlies. When you have the convergence in a surface, there is the form of the free surface is like this, and the isopycnals are in that way here. And due to this thing, you have a first Ekman layer, surface Ekman layer, and then there is interior. In the interior, you can see clearly that there is a vertical shear. Vertical shear means, what means vertical shear? We have seen a few lectures before that this is a thermal wind relationship, or this is the geostrophic balance. So this whole area here is the interior where the geostrophic balance is responsible for the motions, for steady motions obviously, and while in the Ekman layer, surface Ekman layer, there are Ekman balance against steady motion, but where friction plays an important role. While here the friction does not play any role. Certainly wind can also create the setup, wind setup, which means that if you have the wind blowing toward the coast, this is the coast, and the sea level slope this way because there is a transport in the direction of the wind. Partially is the transport in the direction of the wind, and the pressure, the sea surface slope is proportional to the wind stress and the total depth. So this is this kind of wind setup. This is this kind of sea surface slope, which is due to the transport of water in the direction of the wind. As far as the large scale, circulation, or as far as the important vertical motions near the coast, much more important are the divergence in the wind field due to the wind curl or due to the coastal boundary, the presence of the coast, where the wind blows not perpendicular to the coast but parallel to the coast. But we will be talking about this much more. A eastern boundary current is in the northern hemisphere is something which appears if the wind blows parallel to the coast in the northern hemisphere. There is the Ekman transport from the coast to the open sea. Here we have Ekman layer. Then we have the interior, and due to this kind of transport, wind-induced transport, due to the boundary conditions at the coast, that there is no flow across the coast. There is the flow from the coast toward the open sea. There should be the counterflow in the deeper layer, which compensate for this outward flow in the surface layer. So this after the first period of the adaptation of the wind field and formation of the Ekman transport, very easily after some times you get this kind of circulation. As a consequence of that, you have here the vertical motion toward the surface. And then you have the upwelling region, which is the area what we have already before mentioned, is the area where the water is relatively cold and rich in nutrients, which is very good for the primary productivity. And the poleward undercurrent is due to the since we are here talking about the geostrophic interior, therefore below the Ekman layer, poleward countercurrent is due to the geostrophic balance between the pressure at the coast and the open sea. So if you have this kind of wind blowing from the coast, along the coast, leaving the open sea at the right hand side, in deeper layers the geostrophic flow is northward. So in the interior there is a northward geostrophic flow. In the surface you have the eastern boundary current, which is again due to the horizontal pressure gradient. This is how typically the upwelling area looks like. If you go to areas where such conditions are present, that means where the mean wind field is blowing along the coast, this is what we would find in a deeper in a water column over the area. This is essentially the same thing. What is interesting is the climatological response. It's interesting the climatic response, the meteorological response to the presence of the relatively cold water here is that obviously the atmosphere is cooled in that area here. So therefore, the vertical stability of the atmosphere is much stronger here than without this cold water present in the coastal area. The typical dimension of this upwelling region is on the order of 100 kilometers. Okay, so it's a pretty large area. It's not when we are talking about the ocean. Okay, so I mentioned before also the equatorial upwelling. Equatorial upwelling appears due to the divergence caused by the Ekman transport, due to the change of the Coriolis sign of the Coriolis parameter crossing the equator. So you have the northern hemisphere, you have the Ekman transport to the right of the wind, and the southern hemisphere to the left of the wind, and therefore there is the upwelling creates in the equatorial area, simply due to the fact that the change of the sign of the Coriolis parameter creates the divergence. So this is another way of creating the divergence in the ocean. Okay. So these are mainly small scale processes, again generated by the wind field. If there is a strong discontinuity in the wind field, then there will be upwelling, downwelling areas which are approximately 100 meters deep, and these slicks which are formed due to the upwelling, downwelling, and due to the heterogeneous wind field is on the order of a kilometer. So sometimes you can see at the sea surface when you have a strong wind blowing, you can see the areas where there is no there are no ripples. They're very, very smooth. And then you have ripples, and then again smooth. So you see these lines if you have a stronger wind field. This is this is just think what when we. So this is how we. Let's continue with the with the vorticity. Yes.
About the coastal wind.
Yes.
Like you said, usually on the western part of the continent, there is upwelling of the cold water.
Or eastern part of the ocean.
Yeah. For example, if I may take the case of Namibia, well, there is an upwelling.
Namibia is
The western part of
Africa.
African continent, but further down.
Yes.
So, because you said if you have a cold water upwell, it affects the environment by ensuring that the environment is stable and therefore less rain. So could this actually be the reason as to why you have the Namib Desert? And if so, to what extent does it affect you?
If it's so, what is?
If at all, that is one of the major reasons as why you
Yeah.
have the Namib Desert. To what extent does it play the role?
Well, it depends also on the orography, because if you, for example, you have very strong upwelling along the South American coast, but then there you have also the high mountains, and then if you have high mountains and the wind blows perpendicular to the mountains or in a certain angle with respect to mountains, there is the convection, and then this can cause the rain. So if Namibian land is relative no high mountains, then although you have there is the upwelling cold water near the coast, and in addition to that there are no high mountains, so with the fact that the climate is dry, it could be due to that. So it's a combination of the two, the vertically stable air on one hand, and the not present of the high mountains next to the coast, because you have Andes along the South American coast. I don't know, Namibia, I don't. Are there high mountains?
No.
So that's really, and that's part of the problem. So you cannot really explain everything in terms of the temperature of the background of the. So let's see. Now we will introduce the vorticity concept. We'll introduce the vorticity concept, and which is the momentum of rotation, and the processes that introduce changes in vorticity. We are now interested in changes of vorticity because by looking at the changes of vorticity, we can also explain some features of the circulation. And this is what we are looking for. We are looking for the changes of vorticity. So that means that the changes of the components, different components of the velocity perpendicular to the direction. So in other words, if you have if this is V component, if there is a changes of the V component amplitude in the direction of X, then the vorticity is non-zero, okay? And the same thing with the Y component. So this we are looking for the changes of this parameter. So if we start from the momentum equation, how we obtain the vorticity equation, and find out what are the processes which are determining or causing the change of vorticity, we start with the momentum equation, and if we make a derivation of this component with X, and the derivation of this component with Y, and make a difference between the two, what we obtain is we have something which looks mess, but it's not really. It's relatively simple stuff. So we do the difference between this one and that one. This one multiplied by X, the other one multiplied by Y. And by doing some manipulation, we can see that, for example, the pressure gradient term goes to zero, and so we have the vorticity equation, which is this one here, which says that the vorticity changes zeta plus F. This is the absolute vorticity, which is made of relative vorticity, which is the vorticity associated to the velocity field, and we have the planetary vorticity, which is this thing here. So the variability of total vorticity with time is function of these 1, 2, 3 terms, and we will see now what these 3 terms really represent, and how they what they reflect with as far as the processes, as far as the characteristic of fluid is concerned. So we have these terms, and the first one is obviously the rate of change of absolute vorticity following the fluid motion. So because there is a total derivative of time. Then we have the effect of horizontal velocity divergence of vorticity. This is the divergence term. Divergence term says simply this thing. This is the vorticity, right? And if you have the divergence or convergence, that means that you have changes of, for example, on the x component of velocity, changes in the x direction. So this is divergence or convergence. Therefore, this term here shows the effect of horizontal velocity divergence on the vorticity, multiplied obviously by the absolute vorticity term. Then we have this one here, this term here, which is transfer of vorticity between horizontal and vertical components. So this is vertical twisting or tilting term. So it's if the water column is tilting or twisting. And then finally we have the effect of baroclinicity. So that means that we have the influence of the horizontal pressure, horizontal density and pressure gradient in the fluid. If there were no horizontal temperature and pressure gradient, this term is not present at all. So let's look at each term. So this is the rate of change of absolute velocity, which is expressed in this way. So this is the local tendency of absolute vorticity. And then here is a horizontal advection, because the vorticity as itself can be transported into the area by horizontal flow. So, and this transport of horizontal velocity is taken care of by these terms, which is horizontal velocity advection and vertical velocity advection. So this is the first term. This is the second term, which is the effect of horizontal velocity divergence on vorticity, which means that what I was showing you few lectures before, if you have the horizontal convergence, then that means that it will generate the vertical velocity downward, or vice versa. If we have the divergence, we'll have the vertical velocity upward. And so this is this thing. The vorticity will decrease if absolute velocity is vorticity is positive, and vorticity will increase if absolute vorticity is negative. Okay, so. And convergence, then vorticity will increase if absolute vorticity is positive, or vorticity will decrease if absolute vorticity is negative. And obviously everything has to be considered if where we are in a northern or southern hemisphere. And how do we explain this? We explain this in a simpler way. If you have the convergence, then the water column is stretching. By stretching, its radius is decreasing, and you add up the vorticity to the water column, and vice versa. Okay, if you have a squeezing of the water column becomes larger, and then you have the lower momentum of rotation. So this mechanism is very important for large-scale mid-latitude system, but it is important also for some smaller scale areas where you have, for example, the strong sinking of the water column. If you have a strong sinking of the water column, for example, if there is a basin like here in the Adriatic or Labrador Sea, if there is an outflow of the very dense water from the relatively shallow area. When this water leaves the basin, it sinks very strongly, so which creates the vertical stretching of the water column. So by letting enter into the basin dense water, very dense water, very heavy water, it creates the vertical sinking of this water and the stretching of the water column, and then you have the positive vorticity. So this is that's the effect of horizontal velocity divergence. Horizontal velocity divergence, you will see later, it can be created by the wind shear. When we will be looking at the vorticity equation with having the forcing on the other side, we'll see that the main and the most important mechanism which creates horizontal divergence or convergence is the wind, by the Ekman pumping or Ekman suction. Then there is a transfer of vorticity between horizontal and vertical components. This is a twisting or tilting term. For example, this is an example where vertical shear of V component is producing shear vorticity about an east-west axis. This orientation of the vorticity vector is shown by the solid arrow. So you have this thing. Then east-west variations of the vertical velocity twist or tilt the vortex stretch. Changes it. It's not vertical anymore, but it's stretched. It's tilted toward the more vertical orientation. So this is how there is a production of the vorticity by this term here, which includes the horizontal gradient of the vertical velocity and multiplied by the vertical shear of the flow. What is essential in this term here is that there is a horizontal gradient of the vertical velocity, which then produces the changes of the total vorticity, of the absolute vorticity. Sorry. And finally is the term which gives the importance of the baroclinicity on the velocity field. I was looking at the importance in some areas of this term, which is typically 1 order of magnitude smaller than, for example, the vertical stretching or squeezing of the water column. So quite often this term is relatively is not very important, but anyhow it is present and it has certain importance, but typically can be less. Yes?
Why is it called the solenoidal term?
That's a good question. I don't know. I'll tell you. But it's baroclinic term. We call it mainly baroclinic term. Yeah. So. I am used more to the term baroclinic. I haven't heard so many times solenoidal term. I'll tell you as soon as I look through. Okay, so this is these are the different terms of the vorticity equation, and there is one more thing. What the equation what we have written before is the frictionless flow. So there is the only force which is present there on the right hand side of the equation is the pressure gradient form. This pressure gradient form, when you do the manipulation to produce the vorticity equation, practically pressure gradient form disappear. It's zero. If you take into consideration we are talking about the friction, about the fluid where friction is present, then we have to take into consideration the horizontal, the vertical, the friction. So that means that if you integrate this equation from surface to the bottom, at the surface you have to take into consideration the wind stress. And so the equation on the right hand side has now the two components of the wind stress. So you have at the right hand side tau x, and you have a tau y, which is the pressure wind stress. We have done this. We made a derivation of the x with y, and with y component of the momentum equation with x. So on the right hand side, in the vorticity equation, we have a term which is proportional of d tau x dy minus d tau y divided by x. Okay? And this is the wind curve. So the vorticity equation, the vorticity changes, the individual the vorticity changes is also obviously function of the wind curve. And this has to be taken into consideration when we are, and this is why the wind is influencing the large scale motions, because it creates the vorticity, generates the vorticity changes in the verb ocean due to this specific term, due to the curl of tau. Okay? So let's we will come back to this many times. So, as we have seen before, the equations of motion, when we do these manipulations, we obtain the planetary vorticity, which is proportional to the Coriolis, which is equal to the Coriolis parameter, and we have the relative vorticity, which is defined here as the rotor of the vector v. So the potential the absolute vorticity is defined as a sum of the planetary and the relative vorticity. One is due to simply to the position of the particle, whether it is in position, at which latitude is positioned the particles, and the other depends on the horizontal gradients of the temperature. And this is the equation of vorticity equation, what we have obtained before. But as it says here, in a frictionless ocean, there is any force on the right hand side. And so here we have the curl of the wind stress enters into the plane. So in the case if there is no force in a frictionless ocean, this is the equation, or this is the potential equation, which says simply that there is the changes of the vorticity is proportional to the divergence in the current field. Here is simply some definition of the vorticity, or some illustration of the vorticity. This is the horizontal gradient of the vorticity. If you have this kind of gradient of the vorticity, that means that the vorticity is defined as positive. Right-hand rule of thumb is up, which is the positive vorticity. Here is a negative vorticity. When you have the this gradient of the horizontal component, and we use the Greek letter theta for vorticity, and here is there are two vorticity field, two current field, which shows the positive or negative vorticity. Now we are coming to potential vorticity, sorry, where the potential vorticity, like an angular momentum applied, however, in this time to a fluid, is conserved. So potential vorticity is defined as a planetary vorticity plus relative vorticity, as we said before. And potential vorticity has three parts. One part is the planetary vorticity, so as I told you before, it depends where the particles is or water column is present. Theta is the relative vorticity, which is associated to the gradient of horizontal gradients of the temperature. And the third term is the stretching term. The term is practically the depth of the water column, which determines whether the water column is stretched or squeezed. So, vorticity 1 and 2 are called the total vorticity, and the stretching or the height of the water column is in the denominator, since making a water column taller makes it spin faster, and vice versa. This is, as I told you before, if you stretch the water column, it spins faster, and vice versa. There are quite important interpretation or quite important solutions of the equations of motion, where the conservation of vorticity is determined in the wave-like motion. We will be talking about this later, like Kelvin waves or Rossby waves. They are restoring force in those two wave type of motions. Is the vorticity, is the conservation of the vorticity. Okay. So this is the equation of the conservation of potential vorticity, which simply says that the particle that along the path of the water column of a particle in the ocean, this thing is conserved. There is no changes of the ratio between absolute vorticity and depth along the pathway of the water column. If you look at the typical values of the relative vorticity, it can be seen that the relative vorticity is usually smaller than the planetary vorticity. Only in a very strong horizontal gradients of the velocity, the potential, the relative vorticity becomes as important as the planetary vorticity. Like here as an example, we can see in the western boundary current, where there is a strong shear, horizontal shear, where there is a strong horizontal gradient of the flow, we have 1 meter per second changes in 100 kilometers, which is 0.14 cycles per day, which is smaller, again, still smaller than planetary vorticity. Therefore, one can assume that in the first approximation, the water particle should move along the lines F over H constant, because we neglect theta with respect to F, so we remain with ddt F over H is equal to 0. So for large-scale motions where we can assume that the relative vorticity is weaker, smaller than the planetary vorticity. The particle is moving along the f over h constant, equal constant lines. So that means that if we increase, for example, if we increase h, the particle should move toward a higher value of f, and vice versa. If we decrease h, the particle will move to the smaller values of f. So if the particle comes to the deeper part of the ocean, in order to maintain the potential vorticity, in order to maintain f over h constant, has to move southward, and vice versa. Okay, we'll see this few examples of that, how they look like. And here is the potential vorticity balances example with each pair of two terms. Here is the relative vorticity is 0, and here is again the relative vorticity 0. Moving northward from here to there with the same depth, depends whether the depth is the same. If we move if we move northward, we are coming into the area where f is higher. If the f is higher, then that means that the water column has to become vertically larger, has to extend vertically. So the conservation of potential vorticity says that if we move the water particle from northward, then vertical stretching should occur. This is the potential vorticity balance for a Sverdrup balance for a large-scale general circulation ocean, which is this thing here. Beta V is equal to FWZ. Beta is the longitudinal changes of the F. So beta is df dy. This is the first approximation for the vertical, for the north-south changes of f, and this, if we assume that beta is changing, so that means the water column is moving northward or southward for the distance is larger than 100 kilometers, on the order of 1,000 kilometers, we have to take into consideration the north-south changes of the Coriolis parameter. If the water particles is moving north-south on the distances on the order of 100 kilometers, then we can assume that f is constant. Okay? So we are talking about these two, the two approximations. If we considering the ocean, we can have two approximations. One is so-called beta plane, where there is a north-south changes of the f, and then we have f plane. We have a plane where there are no changes, north-south changes of the Coriolis parameter. Since we are talking here, as it says here, we are talking about large-scale general circulation, we have to take into consideration the beta plane, the beta parameter. So we have to consider the beta, and this is obtained, in fact, from the Vorticity equation. You can find it out very simply. This from the conservation of potential vorticity. And so you have the beta V is FWZ. What it says simply, it says that if the particle is moving north-south, the product between V and beta should be should be proportional to the vertical velocity. This is directly what we said before. The vertical squeezing of or stretching depends on a movement of the particles north or south. If the particle is moving northward, the vertical velocity is positive. If it's moving southward, the vertical velocity is negative. So we have a vertical squeezing or stretching, which is due to the fact that there is a beta there, the df dy is different than 0. If the df dy is equals 0, there will be no vertical stretching or squeezing of the water column, because the water column obviously will not be moving in a distance is large enough to provoke this squeezing or stretching of the squeezing or stretching. Here it is the simple illustration of the conservation of the potential vorticity, or the fact that the particle is moving, that F over H is conserved. Consider a bump at the bottom, and the particle which is running in this way. So once it comes to the shallower part of the world ocean, so there will be a stretching of the water column. So that means that the water column will decelerate, will have a lower rotation rate, and that means that it should go southward to the area where the potential vorticity is lower. So F over H has to be constant, and since H is smaller, then F also be smaller proportionally. And also, once when you see in a steady type of motion, the particle or the flow has this kind of turn, that means that there is the deformation at the bottom, which is associated to the shallowing of the water column, to the reduction of the water depth. And so once it passes over the bump, goes back to the same latitude where it arrives to this bump. So this bump and this deformation of the flow field is simply due to the conservation of the potential vorticity, or conservation of the F over H term. Okay. Another thing is also that here, relative vorticity, if these are the lines of if these are the vectors, real vectors of the velocity, we can see that the horizontal shear, the relative vorticity is 0. So that means that theta plus F, that theta is equals 0. And in that case, it's not in the first approximation, but it's in absolute terms. The F is 0. The theta is 0 in this specific case. Okay, this is just an example how the deformation of the water depth changes the flow simply without any forcing. In that case, there is no forcing, there is no wind current influence. And here is the production of the relative vorticity by changing in the height of the water column. In this case, for somebody, if we force the water column, which is present in this specific depth H1, if we force the water column to move toward the deeper area, then what is happening is that the water column is stretching against the positive relative vorticity, and so we have, by simply moving the water column from the shallower to deeper water, there's an addition of the positive vorticity to the water column, since the water column is spin faster in a deeper water, and vice versa. You can invert this picture, and you can see that by moving the water column from the deeper water to the shallower water, then the spinning is the water column, the rotation is reduced because the water column is stretched, squeezed. So this is that's another important mechanism. So if for some reason, also for example in a case when the wind forces the water to move toward the coast, then the water toward the coast, obviously there is a horizontal gradient of depth. This horizontal gradient of depth means that we are forcing, the wind is forcing the water column to move toward the coast, and this then creates the production of the relative vorticity. If we are on a on a beta plane, in this specific case, this water column will have to move northward in order to conserve the potential vorticity. But we are talking here only about the production of the relative vorticity due to the movement of the water column perpendicular to isobats. And here is how practically, due to the conservation of potential vorticity, there is a the waves can be produced. Why? Because in that case the vorticity angular momentum conservation tends to is the restoring force for this kind of movement. If there is a movement from this specific point here northward, there is an eddying or spinning, increasing of spinning of the water column, and so if there is any force here, then the free waves can be formed, and these free waves means that the water column will try to go back to the area where it had the original vorticity, but then due to the movement by inertia passes over the original position, and then reaches a certain point that again it was moved northward and so forth. In this way, there is a formation of waves. These formation of waves are simply due to the conservation of the angular momentum. We will see later that we can obtain from the equations of motion, we can obtain the solution of the momentum equation, which is due to this angular momentum conservation, which are Rossby waves. Rossby waves are on a beta plane where there is a north-south changes of the planetary vorticity, and where simply the conservation of the vorticity is the restoring force, which causes the oscillations, north-south oscillations of the water column. Let's see what else do we have. Oh, okay. Now we have talked about this Ekman pumping, and so far we have been talking about the equations, vorticity equation, where there is no forcing on the right hand side. As I told you before, if there is a curl in the wind field, in that case there is a forcing on a water column. And last time we obtained the Ekman pumping relationship, which is this thing here. And so Ekman pumping relationship, or this is the which simply says that if there is a if there is divergence or convergence of the Ekman flow, there is a creation of the vertical velocity. And vertical velocity doesn't mean nothing else but the vertical stretching or squeezing of the water column. So the wind is, in that case, is generating the vertical stretching or squeezing of the water column, and generating the relative vorticity of the water column. So before we have been talking about the changes of the depth of the ocean depth. There is a particle moving by itself to the different water column depth. Here we are producing the vertical stretching or by the vertical velocity generated by the wind. So here is this is the horizontal divergence of the Ekman transport, which then reflects into the vertical velocity. This equation. This simply says that. So this is and here is the final equation, which says that the vertical velocity is proportional to the curl of the wind stress. Okay. So the larger is the curl of the wind stress, the larger is heterogeneity in the wind stress, the higher is the vertical velocity, and also obviously the sign of this vertical velocity, upward or downward, depends on the sign of the curl of the wind stress. This is exactly what we have seen in a specific examples where there is the convergence of the wind field over in subtropical areas, where there is a convergence in subtropical areas, and if there is a convergence and the wind curl is such that produces the vertical velocity downward, because there is the convergence, there is a bump in the sea surface, and then there is, as a consequence of that, is the vertical velocity in a downward direction. So this is the term which connects the curl and the vertical velocity, which explains this pattern of the ocean's mean ocean circulation, because these terms are on the basis of this thing is a steady solution, because you remember Ekman solution is steady flow, where we have a friction, and we have a friction which then is expressed in terms of the curl of the wind stress, and steady means that we are looking at a very long time scale in the ocean, and these are really what we have seen from the steady motion of the. Okay. Here is what I have just talked to you. You can see again the Ekman layer, geostrophic interior. You have the convergence and divergence. This is the convergence. You have trade winds and westerlies. You have convergence. You have a stretching of the water column. And in the geostrophic interior, there is this geostrophic flow, which is anticyclonic, which is associated to this vertical velocity from the Ekman layer to the geostrophic interior. And so now we go to the conservation of potential vorticity in order to explain the asymmetry between east and west in the world ocean and the presence of the coastal of the western intensification, and how and why it is on the west, why it's not on the east. Okay, let's look at the structure of the wind field. Structure of the wind field is such that introduces the anticyclonic vorticity. So you have anticyclonic vorticity. The anticyclonic vorticity in this specific area here that means that the water column should move southward because the wind is impacting the horizontal vorticity. What is happening on this side here? The wind is impacting the negative vorticity also on that side as well. But in that case here, since this is the closed circulation, the particle is moving northward. But the particle is moving northward. That means that it's moving in a planetary, in an area with planetary vorticity is higher. So that means that the particle is really moving against the potential vorticity conservation law. Therefore, something has to come and help this thing in order to enable this particle to move northward. Otherwise, this kind of thing is not allowed. This is not allowed because here the wind is adding the negative vorticity and the particle is moving anyhow northward. This is not possible, and there should be a relative vorticity which then comes and plays the role in helping the conservation of the potential vorticity. And indeed, in addition to the potential vorticity input due to the wind, there is the formation of the strong shear along the western boundary, strong cyclonic shear along the western boundary. So you have the relative vorticity, which is positive, and the particle has a negative vorticity input due to the wind, and these two things has to, combining these two, the sum should be positive in order to allow the particle to move to the area where the planetary vorticity is higher. Otherwise, the particle will not be able to move northward. It's moved northward thanks to the fact that there is a strong shear. So, on the western side, the strong cyclonic shear area is formed where the relative vorticity is such that compensates for this negative vorticity input from the wind. And in fact, if you look at for example, in the Gulf Stream, which is one of these western intensification manifestations, you can see that at around 100 kilometers from the coast, the velocity is 1 meter per second and more, but close to the coast is zero by definition because the boundary condition doesn't allow the flow to be, has to be zero, although it's parallel to the coast. So you have a strong horizontal shear, strong relative vorticity, but this relative vorticity is positive. You can see that the largest vector is 100 kilometers from the coast and then diminishes, goes to 0 next to the coast. So you have the higher positive vorticity, right? This is why we have this is how we explain in terms of the potential vorticity conservation. How do we explain this asymmetry between east and west? And this asymmetry which is associated to the wind forcing, which then inputs the negative vorticity in the wind field and then creates this anticyclonic circulation, which then these huge anticyclones becomes asymmetric because of the potential vorticity equation conservation. Okay? So, the yellow, let's see what, okay. Why don't we look at the, we will come back to this later on, I think, I hope. But let's now go back to the upwelling. As I told you before, the upwelling or divergence or convergence in that specific case is generated by the boundary condition at the coast. In a along the way, western coast of Africa, as well as along the western coast of South America, it's a very common phenomenon is the coastal upwelling, because on both Atlantic Ocean and the Pacific, there is the southward flow along the western coast of continents. I'm talking about the southern hemisphere, right? So there is the sorry, it's northward flow, not southward. There is this equine transport from the coast to the open sea, because the wind is blowing, leaving the coast at its right, and then you have the surface Ekman layer flow from the coast toward the open sea. And the phenomenon which is happening in South America is very famous. It's very famous because of its long-term variability, because there are situations in which this upwelling is really present, well developed, and but since the part of the economy of these countries are based on the fishery, you can imagine that the upwelling plays an important role in their life. And so in a normal situation, there is the wind blowing this way, and there is the surface flow as we have seen. The thermocline has this shape here, so it's close to the surface or cutting the surface next to the coast. And then it's very deep at a typical depth when you go to the open ocean. The consequence of that is the flow toward the open sea in the Ekman layer, and then you can there is the cold warm water which is brought from the surface, from the coast toward the open sea, and there is a whole area here where the temperature is relatively cold. not only the coastal upwelling appears also along the northern coast, along the California coast, to less extent to the European coast because of the complicated topography. And so this is the normal condition. And normal conditions also means, from the point of view of the atmosphere, that in the area where there is a relatively warm sea surface, there is the vertical convection area and a strong rainfall. In El Nino conditions, El Nino is the phenomenon which means that there is no. El Nino means in Spanish means the baby child, the Christ child, which is because it appears around Christmas. Christmas child, Christ child. And in El Nino conditions, what happens is that the wind which blows in the normal conditions along the coast doesn't appear as strong as it usually is. And as a consequence of that, there is no upwelling along the coast. And the coastal area is relatively warm. So there is no cold area along the coast. And its vertical convection and rainfall becomes closer to the coast, and this situation where there is no upwelling in El Nino conditions, there is an increased convection in the atmosphere and increased rainfall in the atmosphere. You remember why we are talking about the economy, about the importance of the fishery. When there is a upwelling, we mentioned this before, there is the transport of nutrients into the surface layer, then the phytoplankton bloom, zooplankton coming there, and then fishes finally come there. And then the normal cycle means that there is a lot of fish. In this condition here, the quantity of the nutrients is very, very low because the phytoplankton has consumed everything. There is no additional transport of nutrients from deeper layers, so there is no more phytoplankton bloom, no more zooplankton biomass as strong as it here, and fishery relatively poor. So this is how people were really understood and were interested in this phenomenon because it really has a strong influence on their life. So this is the El Nino condition, and this El Nino typically appears every 3-5 years or something. It is rather important to predict the El Nino in order to adapt the life to these El Nino conditions. And
excuse me, Professor.
yes.
So it's not clear to me what is the forcing of these El Nino conditions.
What is the forcing of El Nino? Forcing of El Nino condition can be on the large scale climatic conditions. It's not simply, it cannot be simply explained in terms of what is happening in this specific area. It's much the consequence of large scale atmospheric circulation. Okay, and the perfect understanding of this mechanism is not really clear so far. There are indications, for example, that El Nino event can be manifested or is manifested in a specific climatic conditions over larger areas, not only locally here, but then there are indications that, for example, in Australia there is a larger amount of rainfall. In some African areas can be associated to larger rainfall. Nobody knows. It's not clear what are the mechanisms which are connecting the climatic condition in specific remote areas with respect to El Nino. What is happening? What is the mechanism in the atmosphere? Evidently, is associated with the atmosphere, but how this functions, it's not clear. Here is again this schematic presentation. There is this El Nino this way. There is a normal El Nino. You can see that in El Nino conditions, the vertical convection in the atmosphere becomes closer to the. And then there are La Nina. La Nina is the third phenomenon which is introduced recently, which means the very strong upwelling, where the warm sea surface water has been moved far away from the South America coast toward Australia and so forth, and the equatorial thermocline is touching practically the sea surface. Yeah, so that's how it looks like. The signal which is associated to El Nino comes from the equator. It's moving along the equator, so that means that the signal which is associated to El Nino comes from the Australia and goes to the coast of South America. This is and how this can be explained. This is how the rotation around the high and low is the northern and southern hemisphere. Looks like we have talked about this later. We have talked about this before. In the northern hemisphere, we have high and low, anticyclonic, cyclonic, and the southern hemisphere is the opposite. The thing is that if this is equator and this is east and this is west, this is east coast, this is west coast of the ocean, and this is east coast of the ocean, that means more or less the African coast. There is these highs which are progressing toward the equator, because their direction of progression is in the opposite direction. So they join each other at the equator. But at the equator, there is the high, the unique high is formed, single unique high is formed, and if it stays at the equator, what happens? Along the high, on the northern hemisphere, this is part of the northern hemisphere, there is the anticyclonic flow. The part of the high, which means on the southern part of the equator, the circulation around this high is cyclonic. So that means that in both sides of this high, there is a circulation in the same direction, eastward. So that means that this high is moving along the equator, moving to the east coast. And this is how the signal, whatever is happening on the west coast, reaches the east coast, and this is how the signal associated to El Nino also reaches the east coast. This is one explanation. What that means? That means that if somebody wants to understand and see the arrival of the signal associated to El Nino, has to do the measurements along the equator, but westward from the area of the position where the El Nino appears. Before we just few think how the El Nino manifests in different parts of the North Pacific. This is the American coast, you can see it, and you can. This is the eastern displacement of warm water, and associated rain clouds in gray. I don't like this anyhow, so I won't show you anymore. No, this is terrible. This is much more interesting, and the colors are much better. Okay, this is the consequences of El Nino on different parts of the world ocean. For which we don't know exactly. We cannot explain why there are some phenomena which appear at the same time and simultaneous with El Nino in different parts of the world ocean. For example, in eastern Australia, you can see that's a very dry climate. Next to it is this very wet. This wet is due to the vertical convection because of the presence of relatively warm water. This is directly associated to it. But for example, in a part of India, there is a dry period which is simultaneous with the El Nino conditions. In a December, February, that means that in a direct season of El Nino, you can see that it's very warm in northern America, western and eastern Northern America. There is a relatively dry period between Madagascar and Africa, a relatively wet period around the equator in Africa. Here is a wet period, obviously, because this is El Nino, and then it's but here, for example, this wet period here is not clear why and how directly it's connected with a large-scale atmospheric circulation. These relationships were obtained simply by looking at the correlation between different parameters in the atmosphere and the El Nino, and in a lack of the direct physical explanation, this is also called the teleconnection. Teleconnection means that something what is happening on one side of the Earth is related to something which is happening on the other side of the globe, but the exact mechanism is not really. Yes, somebody has asked.
The El Nino, I thought, was westward transport of warm waters.
It was westward, yes.
But I can see some eastward parts, for example, in South America, which was associated with wet conditions.
Yeah.
Here, when you see the South American coast, the western part of South America, you can see some wet conditions. Is the El Nino causing that? Or
Here.
No,
Here. Oh, the wet condition on the western coast of South America associated with El Nino. This is exactly what I told you before. It's a teleconnection. It's something which is associated to the global or atmospheric circulation. It's not very clear physically how this looks because the El Nino is here, so it's not exactly as not corresponds exactly with the upwelling. That means with the relatively cold water present in the coastal area. So there would not be direct explanation of the presence of the cold water and the vertical convection there. It would be exactly opposite. You know. The atmosphere will be stable, and therefore no vertical convection or weaker vertical convection. So it's not a direct, it's not a known physical relationship. It's something which has been obtained by empirical studies.
So the dry conditions?
Huh?
Is this a numerical simulation? Because I personally come from that blue spot there, and in January it is actually hot and burning, and it's not raining. Actually, the wet season is around November to December.
You are talking about
Africa, the blue spot. Where they say it is
spot
wet.
here.
Yeah.
Yeah.
It's rather dry because oil dry season starts from around January.
Yes, but relatively more rainfall than in a dry season. In that sense, relatively to the average, long-term average, for example. It's a dry season on a seasonal scale. It's dry season every year. It's dry, right? But in the case when you have El Nino, in that case the dry season is not as dry as usual. It's a relative question. I hope so. I think we can stop here.